Thank you. This is for everyone who didn't get enough of me and all of my comments during everyone else's presentation yesterday, so everyone can now get ready to hit back with all their questions. I seem to always get a lot of them, and that's fine. The one note I would like to make, building from yesterday, is I'm very pleased at the number of people who would interrupt or augment their slides in order to say, and as we've seen from Addison's presentations, or as Addison has said, that's great, except that I feel like I'm standing on the shoulders of a lot of other people here, and it's not, Addison 360 Research, and I want to give the rest of my team a lot of credit. Chris Willard, our Chief Research Officer, is not pictured here, nor is Laura Segerval, who's been with us for several years, in addition to our newest addition, which we're very happy with, which is my second main bullet here, which is we recently added Michael Feldman to our team as an analyst. Michael is here, and he's waving his hand over here. Michael, until recently, was the editor of HPC Wire and was an extended member of our team in that sense. He was a partner. I was doing a podcast with him for almost 4 years, and it was a real challenge for me personally as an analyst, because I always had to keep up with everything that Michael knew in order to have these conversations with him on a weekly basis. So he's essentially been an analyst in this industry for 7 years, but doing it with a hat of a journalist on. Very strong addition to our team. He's deep in some technology areas that we liked adding to the team as well. Of course, we're all HPC generalists who have to cover any number of topics, but then we tend to have our areas of specialty as well. I tend to go a little deeper on storage technologies. Chris is a little deeper on interconnects. Michael brings a real understanding deep of processor technologies and accelerators. Plus, he's a prolific and excellent writer, so he adds some bandwidth to our team. Thanks, Michael. You can't go back. Other things that are new from us, obviously you're familiar with us and the fact that we work as analysts, market sizing, forecasting, trend analysis. The key to that for us has always been doing a lot of surveying. Being an analyst, a technology analyst, is a little different for HPC than it is in other areas. If you were going to cover the market for, say, smartphones, and you were an analyst at Gartner or IDC, what you would do is you would call up all the suppliers of smartphones and you'd ask them, can you please tell me last quarter how many units and how much revenue you did for all of your models, and then you would put all of that into a spreadsheet and sell it back to them for $60,000 a year, which is a great way to do business, but in high-performance computing doesn't really work because you're talking about a bunch of different technologies, and what connects them is really this application space that we define as high-performance computing. And if we were to call up some of the big suppliers, an HP or an EMC or a Cisco, and ask, can you tell us how many servers, how much interconnect storage did you send specifically to high-performance computing types of accounts over the last quarter? They have no idea. They really don't know. And if they did know, which they don't, but if they did, they certainly wouldn't be allowed to give us guidance on that because it's below the business unit level. So to give any kind of analyst guidance would violate Sarbanes-Oxley in the US and other requirements elsewhere. So it's not that we don't talk to the suppliers. Of course we do, and we look at their annual reports and macro trends to the extent we can, but you have to compensate with a lot of surveys. And that's what we've been doing together with our partners through Tabor Communications, HPC Wire, for the past 6 years with quarterly surveys going back. We're also augmenting that going forward with our own HPC 500 user organization. This is a big deal for us. We in no way are going to displace Top 500. We love Top 500. We partner with Top 500. Top 500 is fantastic in terms of what is capable at the top echelons of research computing. But it's not exactly demographically representative of the industry at large. When you get into starting to dissect the top 500 list to try to determine HPC trends, you're not getting a good even slice of the industry. Our goal with HPC 500 is to get 500 leading HPC institutions, yes, but to have them demographically balanced across the industry, looking at all the geographies, all of the vertical markets, and all the budget sizes up and down. So we're interested in both large and small HPC organizations. We've got over 100 signed up so far, and we're now getting into delivering some of the benefits to these members, like our first member call is coming up, where we'll talk about issues of importance to them. These organizations get free access to our research. The only cost to being in is that we'd like them to answer our surveys once a quarter, and that provides a lot of our guidance to the industry. Just a little delivery thing for our clients that we've started doing is that we've always been putting out these very lengthy, chewy research reports that are 30 pages long, which are, have a lot of insights in them and are good reading, but not everyone's ready to dive into a 30-page report all the time. So we've started also publishing research highlights in slide format. It's a little more digestible and easier to use for a lot of our clients, so that's some extra work that we're doing. And for everyone in the room, whether you're a client or not, we started a newsletter where you can see what's new from us 2 or 3 times a quarter. We'll put it out. Here's the new research, new podcasts, new articles, new trends, new in HPC 500. And if you didn't get our first episode of that coming out about a week ago, you can sign up at Intersect360.com. Okay, so talking about trends for 2013, this is always a fun topic for me to dive into because it's wide open, but I'd like it to be different each year than it was the previous year. And fortunately or unfortunately, there's a lot that we can talk about building on some of the presentations from yesterday as well as some of the research data that we've done over the last couple of years. I should mention that in addition to this presentation, we still do things like our trivia card sets, which we do twice a year. These are little giveaways we do at the big trade shows, so you can get these little Trivial Pursuit cards. How many of every 12 academic users expect to spend more on HPC in 2014 than 2012? Or what % of current HPC storage systems is object-based? You can get a set of these from me. Those are fun. But informed by our research, we get into these real discussions of trends going forward. Shifts in budget allocations is not one that's come up over the presentations yesterday, but it's one I'm going to start with because we did see a dramatic shift there. Processor architectures and their implications are a very big deal because the industry is on the cusp of another one of these revolutions that can bring you breakthrough performance, but requires some changes to the software model and other implications in terms of personnel expertise. And in fact, we have not only one, but 2 such revolutions going on simultaneously, looking at both the trend with multi-core CPUs as well as the trend with accelerators. We've seen users in all industries worldwide trying to grapple with this right now, testing all the different architectures, but committing to none. In terms of trying to place your bets on what are we going to optimize on for the future. Big data, of course, and its potential for HPC, and then we've got to talk about cloud and what that's got to do with everything. Okay, I wanted to start here because we saw a real reversal in a trend. This comes from our annual budget map data. It's one of the 2 surveys that we do every year. The other is our site census data on installations. Our budget map asks at the top level, well, after we ask how big is your budget in various bands and do you expect it to grow or shrink over the next couple of years, taking your HPC budget total from 100%, what % of it goes to hardware, to software, facilities, staffing, services, cloud computing, and other stuff at the top level. And then, of course, the survey goes on to break these down in other items within each category. So software, for example, could be operating systems or tools or middleware or storage software, application software, and we can study the trends there by vertical market. What we were looking at the past several years is a steady decline in hardware as a % of overall spending. As we watched most other categories, including facilities, was growing every year. And we were looking to see how does that trend continue going into 2012. And all of a sudden we had a sharp reversal in this trend where all of a sudden the % of hardware spending went to the highest level that we'd seen in any of our survey years. And we really did try to find any kind of anomalous explanation for that. Is it just a sample bias? Did we survey a different group of people? Every way we segmented it, this trend came out. It happened in academia, it happened in government, it happened in commercial, it happened in large organizations, in small organizations, in all the geographies. There's no other conclusion other than to say this is a real thing that happened in the industry. So then the next question is why, which of course you don't ask on the survey. It's left as us as analysts to take a look at the why. And what we think is that as we went through these recessionary years, you tried to protect things like people as much as you can, and you get a certain amount of deferral of IT spending. You try to go one more year before you upgrade your supercomputer. And then as we get into 2012, we had some loosening of budgets. Not great in the public sector still. Public sector, government, academia still lags, but it wasn't as bad, right? There was some loosening of budgets. And I think what happened is we had a catch-up year in 2012 where a larger than normal percent of end users all of a sudden went and triggered their upgrade at the same time. So that came at the expense of everything else. The interesting thing will be to watch what continues to happen. A prediction here would be that this falls off again because you've got a higher number than normal upgrading all at once, and then next year you should capture fewer than that. So you might get into where this starts getting to be periodic, and every 3 years in the short term you get a spike in hardware. Facilities, nevertheless, we have to think is an upward trend. Over and over we see facilities as an increasing percent of spending, and the other thing that's happening that's not reflected in this chart is a greater percentage of end users are having to budget for the facilities costs of their machine out of the HPC budget. Another toggle that we track in this survey is this not in budget concept. Any respondent can flag any category or any item within a category is not in budget, which means someone pays for it, but it's not me, right? So there's the question of, do I have to pay for the power and cooling for my own computer? That percentage has been steadily climbing. So as power costs become a greater concern, you get a larger percentage of end users who have to budget for it out of the HPC budget instead of that being a separate IT concern. So that's interesting, and it's something that keeps getting exacerbated by these new trends in processors. So I wanted to start there. Now, as we look at our other major survey, which is the site census survey, this survey basically asks the question, can you please tell us everything that you have installed and how long have you had it? And we look at systems, we look at processors, we look at accelerators, operating systems, storage systems, interconnects. We try to cover all of it. It's a pretty complicated survey for people to fill out, but it's a lot of insights that come out of it. The challenges that we're seeing from end users that have come out of this survey is how to balance all of these flops that you're now getting into the system as a result of multi-core processing for the most part. How to turn that into efficient performance at scale. Because this is a supply-side driven transition, right? I tend to think that end users largely would have preferred that the megahertz just kept going up, right? That would have been an easier thing for everybody than going to multi-core, which introduces this new level of parallelism on the socket. Not that Intel and AMD aren't still putting out excellent processors, they are, but this is yet another new paradigm that we've come across from year to year. And you hit these new paradigms and they require changes in the way that you think about scalability, the way you think about programming, the way you think about efficiency at scale, and how you adapt these applications for this new level of parallelism that's inside the socket in this case. A great way to look at this problem is to look at memory configuration. What we've seen over the last several years is that the amount of configured memory per core in systems has actually stayed relatively flat. It's almost, in fact, if you really want to get nitpicky about it, it's gone up a little bit. It's gone up by 20% or so, which in itself would look like growth. But the implication of multi-core here is that as you keep the amount of memory per core constant, the amount of memory per socket or per processor keeps doubling with the number of cores, and the amount of memory configured per node goes up even more than that. The number of sockets per node has also stayed not quite constant. Two socket nodes are still the most common, although today you'd see a greater mix of four processor nodes mixed in. It's kind of the next common. So the average number of sockets per node has gone up a little, but the real thing here is multi-core. And end users are dealing with multi-core by treating each of these cores as a separate processing element that gets the same amount of memory as any other processor. A little digression I like to make here, by the way, is consider the implication of this with regards to ISV software licensing, where you would take to ISVs the argument that it's no fair that you're charging me per core when we're going to multi-core processors, right? And I'm paying more and more for software. When this data suggests, by the way, that that's exactly how the system is being used, where every core is indeed a separate processing element, right? Not meaning to imply that the pricing should be one way or another, but the usage model in this industry is clearly a per core usage model, as is demonstrated by the way we see the configurations going. Now, the next question is, how sustainable is this, right? Here we are in systems that have been installed since the start of 2011. We actually have the newest data in, and I'm not ready to add it to this chart yet. We're still cleaning data. But systems since the start of 2011 have an average of over 64 gigabytes of memory per node. Is that going to double again for 2012, 2013? Are we going to have terabytes of memory on a node, and is that sustainable? You get a higher percentage of the cost of the system going to memory, and of course the power requirements go up. There's implications with regards to memory bandwidth and application scalability. Now, the other main thing that comes into this is accelerators. This is a very simple chart of what percent of end users here in blue are using accelerators. Now, there's two different ways that we can look at this data. This is the site census view for users describing their top systems to us. Do those top systems have accelerators on them or not? And that occurs nearly 30% of the time. If we go the other way around and ask specifically about accelerators, which we did just recently, and say, forget describing your top systems, are you testing accelerators? Then the number goes up to about 75%, right? So it's quite high. But the incidence of how much of your workflow is leveraging accelerators is quite low. It's, it's in the below 10% usually. What we see in the industry is a large amount of testing of accelerator-based solutions, but a small amount still of wide-scale deployments of accelerator solutions. And this is very consistent with qualitative data that we get every time we talk to end users. And we ask them, hey, have you tried Intel Xeon Phi? Are you testing GPUs? Where are you with CUDA? What do you think of Fusion? And consistently the message we get back is, yeah, we're trying it. We're testing it out. We're trying to see what's going to work, right? We're trying some of everything. So far this is mostly NVIDIA because it's been out longer, okay? So, don't freak out, Stephen, or anything. It's just the CUDA and GPUs, 90% of users who are testing accelerators are testing GPUs. They might also be testing other things, but so far it's been mostly GPUs. When we look at the forward-looking, what are you going to be testing over the next 2 years? It winds up being almost equal GPUs and Xeon Phi, and then AMD is kind of further back in the mentions here. so it's not going to take Intel long to level that out in terms of what people are testing. What people actually deploy, I personally think, comes down to less about the performance of the processors than it does the overall environment that's around them. NVIDIA has done a very good job lowering the tinker point with CUDA. The idea that an academic user can download CUDA drivers and test them out on their NVIDIA GPU laptop brings the tinker point for GPU computing way down. So that's in this corner. In the other corner, you have Intel with the very compelling message that it's all standard x86 tools, which the installed base of all of HPC is really going to like. Okay? It's really difficult to forecast which of these models plays out, but I think it's going to be in the software that this war is won or lost, and is really the most important trend for 2013 going forward. So challenges in these architecture trends: power consumption, cost of memory, new models of parallelization, the languages, the programming models are all things that I've talked about before, up to this point. Well, programming model in particular, is MPI even adequate here? This is a great question for the industry. Are we still doing MPI here in 3 years or what? And I ask this question a lot, and the most common answer I get is, right? The second most common I get is maybe MPI plus, which is to say that we need some sort of extension to MPI, but that's not well defined at this point. So I think if something like Swarm comes up a lot also, the idea that you can have an abstraction layer over top that handles whatever architecture is underneath is maybe a nice idea, but we're still in early days. Now, what's clear, let me come back to what's clear. Let me finish the number of bullets first. System efficiency, I put a lot of flops out there. How many am I actually going to use at scale is a question. And then the implications of personnel is a really interesting one. Every different change that we've seen in system architecture, going from vector to SMP to cluster and Windows to Linux, have all had these implications of what it means to be a programmer and what it means to be a system administrator, right? As we went from SMPs to clusters, the role of the administrator or the integrator really changed to where you used to think about it in terms of how much do you know about the operating system. Because in the SMP world, a supercomputer is a relatively self-contained device. And that all got disaggregated in all these separate pieces. And the admin in the cluster world, it wasn't as much about how much you could master the operating system as how much you knew about the middleware stack, right? And getting consistency and scalability in all your middleware tools. As we go forward into multi-core and potentially accelerators, now you get into a lot of questions about system efficiency that weren't necessarily part of the discussion before. How do you do with job scheduling, job placement, job management? What's going to be the role of these middleware providers who have commercial tools for these? Or are we going to, is this really rocks that we're going to use for this? I don't think so. I mean, it will be in some cases, but I think there's a lot of implication there for the tools. Now, I was coming back to what's clear is that we've got to do something, because the notion of just saying I'm going to ignore it and keep doing more of the same isn't really there, because the processor roadmap is going to march on regardless. Right? The option of more of the same is not really there for the broad cluster space. Now, obviously, I'm leaving out other architectures here. I've left out the shared memory architectures or MPPs or vectors, which are still part of the industry, of course. But I'm talking about the broad cluster space here. You're going to have to optimize for something. This is the saying, whether you would seek it or not, war is upon you, right? And you're going to need to choose an architecture and start trying to optimize for it. This is all going to play out over the next year or two. Okay, I got a little double logo on this slide that I didn't notice. Technical versus enterprise computing. This is a slide I would often do at the start of a presentation when I'm defending why do we bother tracking HPC separately from enterprise computing. And I'm coming to it now as I transition to talk about big data and the role of HPC and why it's important. Just at the top level, technical computing versus enterprise computing, the reason we tend to look at these separately is the be good. Different buying behavior in the different groups, technical computing versus enterprise computing. Technical computing, first of all, on both sides, we tend to hear the phrase mission critical. And that's interesting to me in that you can argue mission critical on both sides, but it's one of these definitional areas where it means two different things. In technical computing, you tend to see mission critical from the standpoint of technical computing being linked to whatever the top line mission of the organization was. So if you're Toyota, you buy a lot of computers for a lot of different things. The ones that you're using to design new cars, trucks, and minivans are technical computing. If you're British Petroleum, you own a lot of computers. The ones that you're using to find oil are high-performance computing. And this can be said for the National Cancer Institute and curing cancer, or the CIA and spying, or the Department of Defense and blowing up the other guy, right? Whatever your top-line mission is of your organization tends to be where you're deploying technical computing for that scientific and engineering advancement. Enterprise computing, by contrast, is more about keeping your business running, and is mission critical in the sense of, if my website goes down, I can start counting by the minute how much money I'm losing. But I'm not in the business of just running a website or maintaining an email system or a payroll database or an ERP system. These are things that are mission critical in the sense that I need them in order to operate my business, but they're not directly linked to my top line revenue. And as a result, technical computing year after year we tend to see is driven by price performance, essentially. Now, it's different metrics of price performance in terms of how I measure that, but I'm still, in almost any case, looking for so much bang for so much buck out of my budget. Whereas enterprise computing, year after year, tends to be driven more by reliability. Another way to say that Chris Pop said once, and I've been quoting ever since, is that in technical computing, the watchword tends to be, once you solve the problem, it's no longer interesting. Which is to say, you don't need to build the same bridge twice, right? You've designed the bridge, you go on to the next one, you fold the next protein, you simulate the next weather pattern. Whereas in enterprise computing, the watchword tends to be, once you've solved the problem, for God's sakes, please don't touch it, right? There's very little incentive for the payroll database is working. I don't want to rip it out and replace it with something else. I don't need it to run faster. I need it to just still run. And as a result, in technical computing, you tend to have a relatively higher incidence of new technology development, new algorithmic development, newer, faster adoption rates. Enterprise computing, it tends to be relatively slower. You have legacy systems that hold on for decades that would get replaced faster in technical computing. This gets important as we look at why big data is such a big deal. Now, big data is another one of these areas that we need to get definition around. Anyone talking about big data should put up a definition. No one gets to have a monopoly on what the definition is. Andy did a great job yesterday of talking about how much of this is a buzzword versus how much of it is real. There's tons of buzzword around big data. We as analysts have to define it so that when we're up here talking about it, you know what we're talking about. So, if you want a different definition of big data, enjoy it. This is what we're going to talk about here. And ours is a very user-based definition. It's a very inclusive definition. We tended to approach it from the standpoint of, if we ask a group of users, do you have a big data problem? And they raised their hand and said yes, then we would try to incorporate it into our definition and ask them, what are they doing? it's not a specific technology, which is another thing that's fun from the analyst standpoint. It's not something like a smartphone that you can go out and count. You don't go out and buy a big data, right? Which makes the question really funny. People will ask, what's the size of the big data market? Think about the question for a second, right? What specifically do you want me to count, right? As analysts, it's our job to count things, but the big data market is not a really well-defined concept. Even if I narrowed it down to certain types of analytics applications, which would already be narrowing the question, am I going to count the total market for all servers, storage, and interconnect infrastructure that ever runs analytics? Right? Or do you want the increment of how much more of that stuff would be sold because of big data type trends, which, is, again, a really fishy question. So big data is not a specific technology. It's not even a specific application type. We think the best way to talk about big data is that it's a set of trends, right? Where what you're fundamentally looking at is that the growth in the creation and accessibility of data, which is coming from a lot of different places, is stressing out organizations' ability to manage that data or to gain a competitive advantage based on that data. And if you take that inclusive definition, it picks up a lot of analytics and data mining. It picks up things in complex event processing, MapReduce, of course, but doesn't, it's a lot more than Hadoop, right? It's a very inclusive definition. And the important thing here is that it has a lot of different dimensions to it. You get more data, more types of data, faster ingest of data. You get the dimensions around large files, many users of the files, the rate of ingest, the lifespan, whether it's very long or very short. And you also bring in this notion that you have to allow for the fact that there are entry-level big data problems just like there are entry-level high-performance computing problems. The big in big data is a relative term, like the high in high-performance computing. There's not any Disneyland, you must be this tall to ride this ride. It's not measured in some magic number of bytes where you say, once you cross this line, congratulations, you're doing big data. And when you look at this in the context of some of the presentations yesterday, our bent in this group is to have a supercomputing mindset and to say, well, Oak Ridge National Labs have been doing big data for years. Look at how many petabytes we have. Okay, I get it. It's a lot of bytes, but that's not really what we mean by big data. In this case, what we're talking about is the number and the sources and the creation of all these files. Is that creating an operational challenge? And it is, but you need to define it that way in order for that to count. And then you have to be open to the enterprise that's more in the mid-range, that has 100 terabytes of data in a small cluster, but they're getting data from more places now, and they're having trouble managing the data at the rate that it's being created or accessed. The other implication that's here with regards to big data is this whole notion of if data then value, which has been touched upon but not really elucidated this way in some of the other presentations up to this point. But this is the concept of my neighbor dug in their backyard and found treasure. I want to dig in my backyard and find treasure, right? Which is the whole promise of big data analytics in a lot of these areas. And Eng Lim was talking about haystacks and needles in haystacks. And the big thing is, a lot of the time you don't really know what you're looking for. You just know that you're looking, and you hope that it has value when you find it. And often it does. But this is tantamount to, hey, look at these great people who had these knitting needles and made sweaters and now they're not cold anymore. That's so high value that what we've got to do is give everybody knitting needles. Who can start listing the holes in this argument, right? One is you can give someone knitting needles, they might not have, Yarn, right? You need to be in possession of the data in order to do something with it. Second is they have to know how to knit, right? A lot of this big data stuff, your analytics, it's not like magic that the computer just does it. You have to know questions to ask. Your algorithms are only as good as the analyst who's asking the questions and looking at the data. Because I'll give you a secret. When you start looking for trends, the first ones that start popping out that are really obvious are the ones you already knew anyway. Okay, that Wikipedia map that Ang Lim showed, it was an impressive graph, but first of all, I didn't know what I was supposed to do with the information, right? The number of times countries are paired together by year in a Wikipedia article. It was a pretty graph, but I didn't know what I was supposed to do with it. The second thing is you'd notice that the big correlations come with things you already knew. Gosh, you get a lot of lines between countries when they're at war. But you already knew they were at war. What are the more subtle things that you could get out of that, and how valuable are they, right, is the next question. The third thing, going back to my knitting metaphor that I came up with this morning, and I've decided I'm sticking with it, is, all right, so you've got knitting needles, you've got yarn, you know how to knit. The next question is, are you cold? Right? Because if you weren't cold, then there wasn't a lot of value in the sweater. I guess you could sell it, but this if data then value proposition is at the nexus of a lot of big data deployments, and you have to realize it's a big leap of faith, and is why the ROI argument a lot of the time has to come out of the conversation, because you don't know what the ROI is, okay? Now, you do know that you're trying to get ahead, right? And you can sell it the same as we were talking yesterday about quality and manufacturing, right? You can sell it based on what is the most important competitive thing to you as an organization. And what if you had knowledge that would help you maintain that competitive advantage? Wouldn't you want to take advantage of that? It's a worthwhile investment, but it costs something. And that's the road that you're trying to lead people down. Okay, now where we get into these funny things with big data is, as enterprises are trying to scale their data infrastructure, there are a lot of implications here for different technologies, file systems, interconnects, operating systems, cloud. A lot of this comes down to I/O scalability at some level, or how do I get my algorithms to scale? This has been a major thrust of our research over the last year, and we're going to repeat our big data study this year. Last year, we surveyed hundreds of end users across both HPC usage base as well as a non-HPC enterprise group, a business group, and asked them the same questions about big data and what the implications were. Some of the top insights that came out of the study, we could back up all of this with charts, but first of all, it would take 6 hours, and second of all, you all didn't buy the study. So practical implications there. But top 3 insights that came out of it that I would try to get across to anybody. 1, big data is much broader than Hadoop, okay? So why all the zeal around Hadoop? Well, if you come at it from the standpoint of, tell me the killer app that's really growing, Hadoop is the only one that fits the bill, right? Hadoop is the most commonly deployed application. It is growing the fastest. But as of the time we ran this survey, which was about a year ago, Hadoop was deployed in about 15% of big data workflows, 1.5, which in that sense makes it the biggest brownie in the pan, because nothing else was that big. But there's 85% of the brownie pan that's not Hadoop, right? The Hadoop is one specific solution for one type of big data problem. But if you approach the market from, are you doing big data equals yes, now what are you doing equals Hadoop, it's small. The big unexplored opportunity that's much broader than that is if you added up everybody who's running in-house algorithms. Those are little atomic brownie crumbs that are inherently one-offs. It's hard to go say, I'm going to optimize solutions for people's in-house algorithms, because they're the only one running them. But those collectively amount to 50%, 50, of the big data market. And it was 50% among the technical group, the HPC group. Actually, it was 49. And it was 50% among the enterprise group, the business group. Equal. It was if you think about it that way, the story around helping people optimize their own internal algorithms or their internal applications, especially on in-house data, which is the #1 source of big data, that's 3 times the size of the Hadoop opportunity in this market right now. That's where most people are starting. I'm trying to write a script to manage all of this data that I suddenly have. Now, this might have changed over the last year, and I'd say we're going to resurvey it. But I'm going to stand by the notion that it's much broader than Hadoop. Now, it's also a big deal because there's a lot of money being spent on it. And what I liked about Andy's buzzword presentation yesterday is after establishing that, yes, it is a buzzword, he did go on to establish, and yes, by the way, it's real. And here, we totally agree, right? Out of all the buzzwords that have ever come through this industry, the one that offers the most significant, real, actual growth, revenue, spending for HPC technologies is big data. We found that on average, respondents who are saying, yes, I have a big data problem, on average, they're spending 25% of their IT budget related to big data in 2012. Not 25% of their HPC budget, not 25% of their storage budget, 25% of their IT budget going to big data. Now, there's a sample bias error here, right, which is that we're talking about people who said they have a big data problem, which isn't everybody. But once they say they've got one, 25% of IT budget going to big data is a lot of money. It's a huge opportunity. And why it's huge for HPC in particular is related to our third point on here, which is the performance mattered even to the non-HPC business respondent. When we asked them, respondents, to rate pain points or problems or what they're looking for in their solutions, and there were included fields for things like reliability or personnel or data center issues, but the things that kept coming up, #1, over and over again, had to do with performance and scalability, particularly I/O scalability. Although the definition of I/O scalability would vary depending on what you were talking about. It might be I/O bandwidth, it might be latency, it might be IOPS. But these performance characteristics were bubbling up to be the #1 purchase criteria, even in non-HPC accounts who were looking at big data, which the first thing you do is you go, we've never seen that before. Because go back to my previous chart about technical versus enterprise. Enterprise is always supposed to buy based on RAS, except that the whole premise of big data that you come to realize is that big data is defined by my organizational ability to manage all this stuff has gotten stressed out. I can't just do more of the same. This is another of these situations of the revolution is upon you. You must do something new. Your system is broken. You have to invest in something else here. And this has implications for technologies that are nascent in the HPC space, whether they're faster interconnects or shared memory or faster processing or data management for things like parallel file systems. These technologies have ways that they can be sold in enterprise computing accounts. Now, you can't just shuck everything else and say, no, all you care about is performance and it doesn't have to be reliable. All right? You're still going to need to meet these IT hurdles in order to get in there, which is why companies like IBM have had a lot of strength in selling analytics, because they're already a big trusted enterprise provider and they say, here's our analytics solution, so they start getting in there. But nevertheless, for companies that have their home
in the HPC space, there's still a huge opportunity to say, we can bring in solutions here that will meet your IT requirements but still solve this problem. So big data is going to lead to the adoption of HPC in more areas, and as we're preparing our new 5-year forecast, this is something that we're talking about within our own organization for how much of this needs to be defined as HPC and as part of our forecast, or is it a new non-HPC market that we don't forecast, but a lot of our clients can go get it. There's a semantic argument there that we have to have, so bear with us as we figure that out. But want you to get the point that the opportunity is there. Okay, so now clouds. This is a little cartoon slide here. Two things. This is a slide I used at the final eFiscal workshop. The European Commission had an in-depth economic study of the viability of creating a national or continent-wide scientific public cloud research and what would be the economic models of that. And they had their final workshop in Amsterdam in January. You can find it at efiscal.eu. I was pleased to participate, contribute some data to it. They did an excellent economic job on it, by the way. And this was an exact slide that I used during one of my presentations there. The first is on cost models. When you put together cost models for public cloud computing in HPC or otherwise, you need to understand that how many of the costs are allocated into your economic equation has a vast impact on what you can afford to resell a cycle for, which is an economic way of saying, when I was a kid, I had a paper route. Okay, and a lot of kids my age would have them. The way you got around child labor laws is that technically the newspaper company sells me the newspapers and then I'm selling them to the subscribers. They bought them for 25 cents a paper. I had to pay 18 cents a paper. So the 7 cents profit is mine, and I would deliver all of the papers and then go around on Sundays and collect money for them. So that's your basic model, and then you get tips aside. It's a nice job for a 14-year-old boy. Now, I'm an enterprising kid even then, and sometimes because vacation holds got confused or whatever, you'd have 2 or 3 extra newspapers in your bag. Now, the process for returning those and not paying for them was hopeless, right? It was not what was anything was worthwhile, okay? So essentially, it's a sunk cost. What I would do is, I'm done, I still have a few more minutes before school, and there's a busy street corner right there. I can walk out onto the median and hold the newspaper in the air, and it'd take me a minute or two, but I've sold the extra papers. Question number 1 is, what is my profit on those papers? Okay? And most people would say, well, it's 7 cents, just like all the other newspapers, which doesn't appreciate the fact that that newspaper is a sunk cost that I've already bought. And my opportunity cost of going back home and throwing it away, right, already allocates that 18 cents. So really, my full profit is 25 cents plus tips if I sell that newspaper, because I already had it, I own it. So now that's going so well, and I'm selling them so quick on the street corner, I think I should intentionally ask for 10 extra papers because I know I can go down to the street corner and sell them. So I start doing that. Question number 2, what's my profit equation on the next 10 newspapers? Most of you are nodding and saying it's 7 cents again. It's actually a little worse than that. It's 7 cents minus the risk equation that I don't sell them all, right? Because now I'm intentionally investing in infrastructure for the sole purpose of reselling it, and the overhead is mine. Now, when you look at public cloud with regards to IT, there's a question of how much of the hardware is already invested in, how much of the people are already invested in, how much of the software is already invested in, and how much of those costs are being allocated into your cents per core that you're offering to the end user. And I'm not going to go any farther other than to say that the cost equation is different if you're looking at an Amazon versus someone like an R Systems or Penguin On Demand or SGI Cyclone, a real HPC provider that's investing in it, versus an academic HPC site like University of Texas reselling cycles off of their supercomputer to community partners. Those are very different economic models that are hard to compare. And coming all the way down to what's a fair cents per core hour, you have to appreciate all these differences. Now, my other direction is on barriers with regards to public HPC cloud. Let's say that I woke up this morning and I decided I've evaluated all the benefits of the job and I would really like to become the Queen of France. I've done a thorough analysis of everything I get to do if I'm the Queen of France. I'm sold. I think this is a highly desirable thing. Sign me up. What are the barriers to that happening? Well, there are many, right? Addison, you tell me quickly, you can't be the Queen of France. Well, why not? Well, you're not French and you're not a woman, so forget it. Gosh, I'm all depressed. I really wanted to be the Queen of France. I walk away, feeling bummed out. But I wanted to be the Queen of France so badly that I come back to you 2 years later and say, good news. I wanted to be the Queen of France so badly, I've had gender reassignment surgery and obtained my French citizenship. I'm ready to be the Queen of France now. And you look at me all astonished and say, you can't be the Queen of France. Why not? Well, because you're not of royal descent and France hasn't been a monarchy in the last couple hundred years. Well, God damn it, why didn't you list that among my top 2 barriers to begin with? Right? Here's where we are with cloud and HPC, okay? Everyone keeps citing security and data movement as the top 2 barriers, and they are the top 2 barriers when you look at what % of respondents list them as a significant barrier that's really hard to overcome. But they are 2 out of a long list of barriers, all of which get pretty high rating. And they get into things like managing or redoing my software efficiency or having the product capability or the what it costs or corporate policy. Okay? Now, these hit in different ratios according to who you're talking to. But it's a long list of barriers. And my point of all this is that with regards to HPC and cloud, it's not necessarily about convincing someone that the benefit is there. I could be sold on the concept of the desirability, but we still don't see a really high penetration of spending of HPC applications on other people's cloud because it's too hard, right? In most cases. Now, we do see some. The case studies are going to keep coming out. In most cases, the success stories that you see are either entry level into HPC, where I don't have an existing infrastructure, and I'm using the cloud instead of building out an infrastructure. Or 2, I might be running at peak capacity and occasionally need to burst over it. So I get some cloud bursting, I get some entry level, but both of those are low volume by definition, right? They're both low volume use cases. There is a market for HPC in the cloud, but it tends to be low volume. And you saw the spending and how much there was, and it's not really growing that much. And utility computing's been around for a long time. This is the newest instantiation of utility computing, which has existed in HPC for decades, okay? So there's going to be some of it, but it's not a huge market. And the reason it's not a huge market is because of these barriers. Is there something else I was going to say about that? No, I think that does it. Okay, so with regards to big data, there's a when trends collide problem here. Okay? You run into plenty of organizations where they have a major big data initiative and they have a major cloud initiative. And it's desirable to say, I'd like these to combine. How do I do big data in the cloud? Well, we found there are just as significant hurdles for big data in the cloud as there are for traditional HPC in the cloud, and about similar deployment. What this means is if you're going to talk about big data in the concept of doing it in public cloud, I would be careful as to how to approach that, right? Certainly for HPC or big data, you want to be able to discuss cloud in the context of your overall solution. I've been talking about public cloud here. Private cloud, entirely different matter. Private cloud is all about how I manage my own internal resources, and a lot of those barriers go away, okay? So the moment I needed to talk about my solutions with regards to cloud, whether for big data or HPC, you say, absolutely, I get that cloud is something that you want to do. Here's our cloud technology for managing your own internal systems efficiently and allowing you to burst out to public cloud resources as appropriate, which is going to be very rare, but you don't have to say that last part out loud, right? You have to allow it to be part of the solution without completely subsuming everything you're talking about into it. You know, going back a few years ago, I gave a presentation at HPC where one of the major trends we talked about was Microsoft was growing in HPC, and it was. And we thought they were going to continue to grow. The key change that Microsoft made 2.5 years ago is they announced their technical computing initiative and put all of HPC underneath Azure. And if it wasn't in Azure, they weren't going to be interested in it. Well, Windows in HPC was enough of a hurdle. Azure in HPC was too much. And after they did that, we saw almost nothing of Windows in HPC again after that. It was too much of a hurdle to do everything all at once. So if cloud is a priority, absolutely you want to invest in the management software to coordinate this, but bring public cloud in and don't commit to, yeah, we're going to offload everything to Amazon or whatever your other public cloud, because that data movement, the latency there will kill it most of the time. It's big data, right? Okay, so some conclusions, wrapping up. This is really another one of these points where we're at a revolution point in the industry for a new paradigm for breakthrough performance. And I don't mean to be slagging on any type of process. Just the number of flops that come to the game with things like Xeon Phi or GPU computing are game changers. And we saw it with clusters before, where you could put up every argument you wanted to about clusters being inefficient relative to SMPs, and users go, that's a lot of flops. I'm going to buy them and then figure out later how to program for them, okay? And we're going to see that in this industry. But there are significant implications for how to make these solutions efficient. And the game has changed again in terms of the personnel expertise and the solutions expertise necessary for this. And this has implications for integration services. It has implication for administration services, programming services. I think we're going to see this services category picking up, right? What can an integrator do for you in order to deliver an efficient solution is going to be a very relevant question, point for both government and commercial. There's a huge opportunity to expand the use of HPC technologies. Big data is another revolution here. I really do think we're going to see breakout opportunities for certain categories of HPC technology. And big data is a bigger near-term opportunity than missing middle, which I didn't really even get to in all of this because I made most of my comments yesterday anyway. But, you know, funny point I'll make just wrapping up is another of my favorite questions is what's the size of the market for the missing middle? By definition, it's zero, right? They're missing. As soon as they buy something, they're not part of the group. I think what you mean is what's the potential market, right? How many people might buy something? But the current size of the missing middle is always zero by definition. But big data is the bigger near-term opportunity because missing middle is another one of these things that even to the extent that you create new entry-level adoption, it's low volume. You know, Josh Portner yesterday said some great ideas for how to help people adopt HPC the first time in terms of giving them on-site expertise, helping with software. But that's an awfully high cost of sales equation if you're a big vendor in order to develop someone who might buy an 8-node cluster. Yeah, you're investing in a long-term customer, but it's cheaper to let someone else develop that customer and then steal them at generation 2, right? So that's the cost of sales problem that the vendor community is trying to deal with in terms of developing this missing middle or this entry level. Big data is a larger near-term opportunity, although they're both fun to talk about. Okay, I'm at the end of my time. I always feel like with something like this, I'm starting conversations, and I'm happy to continue them by taking questions, by come get me at lunch. Also tomorrow, the last thing on the agenda is I get to moderate a really fun panel with Analyst Crossfire again. Those of you who've seen it before, we do it as a 30-minute TV program. The topics and the clock will be up on the screen, and in 30 minutes, we're landing this plane. 4 panelists, 2 vendors, 2 users, 7 topics, 30 minutes, and it goes like this, and it's fast-paced. For those who can't stay till tomorrow, Rich Bruckner does produce that for InsideHPC, does the whole video production, and you'll be able to find it presumably on InsideHPC eventually, right, Rich, as well as on our own website. So do come back and look for that. Thanks very much, and I look forward to ongoing conversations.
You gonna take a break?